Welcome to my channel. I'm Zhangjing Xu. Let's look at the problem 32 in chapter 31. Chapter 31 is about Maxwell equations and electromagnetic wave. So first one, tell us this is a follow-up for example 31/1, right? So you just look at the description about example 1. And we found, this is circular parallel plate capacitor. So we draw the picture, look like that. And we know the electricity is moves to the key directions, just the current direction. And the magnetic fields do that in circles, right? So rotate in circles. This one we can say the direction is as a phi if you use a polar coordinates. Now first we'll ask you, find the Poynting vector S points radically inward. So now, as definition, we know the Poynting vector can be written in this equation, right? 1/μ0 E cross B. And now we input E and B inside. We find this is just a key cross phi, right? By the polar coordinate, you can know this is just a negative R. Likely we find, this is just a radically inward. See, R is outside, right? R is this way. But now negative R means it pointing inward. So part of A is proved. Part 2, integrate S over the cylindrical boundary over the capacitor gap to show that the rate at which energy enters the capacitor is equal to the rate at the electrostatic energy is being stored in the electric fields of capacitor. Wow, it's so long, but we can work out it. It just tells you what to do, right? First one, we do integrated S over the cylindrical boundary. So now first one, we need to write down the magnitude of the Poynting vector S. As we know, the magnitude is EB divided by μ0, right? So we write EB divided by μ0. It tells you ignore fractioning of E, so the B can be written in this way with the electric fields. This is by Maxwell equation, right? Now we input the B inside, we get the S Poynting vector is a function of E, right? And now we do it tells us integrate S over the cylindrical boundary. So we do the integration. So now integration looks like this one. So S dot dA, right? Now we can say this direction is we can write it in magnitude S dA, and then we can see S is not changed with this region. So S is put out, and the region in this capacitor boundary, this cylindrical capacitor boundary is 2 pi R0. This is a circle for this capacitor times D, right? So this is the areas in the gap for this capacitor. So we get it there. So we did the first part. Second part, to show that the rate at which energy enters the capacitor is equal to the rate at which the electrostatic energy. So now the static electric energy. So now we can first one write down the energy intensity, right? So energy is the energy intensity times the volume for the capacitor is amount of energy stored. So first we write down the energy density, and so the energy is stored. We can see we write it there. Means the density times volumes. Volumes can be pi R squared and D, right? So now U is this way. Now it tell you to the right at the energy stored, so you use du divided by dt, so you get it there. Now you need to prove, is this two equal? And you prove term by term. Yes, it's equal, so proved. Thank you.